Welcome to Inorganic Chemistry. Today, we are going to explore one of the most fundamental concepts in atomic structure, the Aufbau principle. If you have ever wondered exactly how electrons arrange themselves around a nucleus or why the periodic table is shaped the way it is, this is where it all begins. We will learn the rules electrons follow, and just as importantly, we will discover when and why they break those rules. Let us dive in. To understand how electrons behave, imagine boarding an empty bus on a cold, rainy day. Naturally, you will grab the seat closest to the heater at the front. Only when those seats are full will people move to the colder back seats. Atoms work exactly the same way when taking in electrons. The seats are the orbitals and the heater is the nucleus. Electrons are inherently lazy. They always want to be in the most stable, lowest energy state possible. Therefore, they will always fill the lowest energy orbitals first before moving to higher ones. Now that we understand the basic motivation of an electron, let us look at the formal principle. The word Aufbau is not a scientist's name. It is a German word meaning building up or construction. The Aufbau principle states that in the ground state of an atom, electrons fill atomic orbitals in order of increasing energy levels. The ground state simply means the most stable arrangement, where no extra energy has been added. This systematic building up allows us to write the exact electron configuration for almost any element. This brings us to an important question. How do we actually know which orbital has the lowest energy? We use a mathematical guideline called the N plus L rule, sometimes known as Madelung's rule. Conceptually, this formula estimates the energy of an orbital based on its distance from the nucleus and its shape. In this formula, E stands for the energy of the orbital. The variable N is the principal quantum number, representing the main shell. The variable L is the azimuthal quantum number, representing the subshell shape, where S is 0, P is 1, D is 2, and F is 3. If two orbitals have the same sum, the one with the lower n value fills first. Now that we have our mathematical rule, let us visualize it. What you are seeing here is the diagonal orbital filling diagram, which perfectly maps out the results of the N plus L rule. Notice the columns representing the S, P, D, and F subshells. By following the diagonal arrows from top to bottom, you get the exact sequence of orbital filling. The order goes 1s, then 2s, then 2p, then 3s, then 3p. But look closely after 3p. The arrow points to 4s before it reaches 3d. This might seem surprising, but it is exactly what our formula predicts. Before we move on, let us see this rule in action with a concrete example. We need to determine the electron configuration for potassium, which has an atomic number of 19. This means a neutral potassium atom has exactly 19 electrons. After filling the 1s, 2s, 2p, 3s, and 3p orbitals, we have used up 18 electrons. The 19th electron must choose between entering the 4s orbital or the 3d orbital. To find the correct configuration, we will apply our N plus L rule to both options to see which one provides the lowest energy state. Continuing with our example, let us calculate the energy score for the 4s orbital first. We know that the principal quantum number N is 4. Because it is an s orbital, the azimuthal quantum number L is exactly 0. We substitute these exact values into our formula. Adding 4 and 0 gives us a total energy score of 4 for the 4s orbital. However, this number by itself does not mean much until we compare it to our other candidate. We must perform the exact same calculation for the 3d orbital to see which one wins the electron. With the 4s score calculated, now we evaluate the 3d orbital. Here, the principal quantum number n is 3. Because it is a d orbital, the azimuthal quantum number L is exactly 2. Plugging these numbers into our equation, we add 3 and 2, which gives us an energy score of 5. Since 4 is strictly less than 5, the 4s orbital has a lower energy level than the 3d orbital. Therefore, the 19th electron of potassium goes directly into the 4s orbital. This leaves the 3d orbital completely empty, physically confirming the order we saw in our diagonal diagram. So we have proven that the mathematical rule works beautifully for potassium. This brings us to an important realization. The Aufbau principle is a strong guideline, but it is not absolute. While it works perfectly for most of the periodic table, it fails for certain transition metals. The most famous exceptions occur when an atom is just one electron away from having an exactly half-filled subshell or a completely fully filled subshell. Nature loves symmetry. To achieve this highly stable state, an atom will sometimes borrow an electron from a lower energy s orbital and move it up into a d orbital, directly violating the strict filling order. This exception leads us to ask, why does nature prefer these half-filled or fully filled states so much? The answer lies in something called exchange energy. This is the energy released when electrons with the same spin swap positions within degenerate orbitals. A perfectly half-filled d subshell has maximum symmetry and maximum exchange energy, making it incredibly stable. This extra stability is so powerful that it compensates for the energy required to promote an electron from the s orbital. It is a beautiful reminder that in chemistry, physical stability always overrides simple mathematical guidelines. To see this limitation in practice, let us look at the most classic example, chromium. Chromium has an atomic number of 24, meaning it has exactly 24 electrons. First, we will write the expected configuration using the standard N plus L rule. We account for the first 18 electrons using an argon noble gas core. According to strict Aufbau rules, the next 2 electrons fill the 4s orbital, and the remaining 4 electrons go into the 3d orbital. This gives us an expected configuration ending in 4s2 3d4. But as we just learned, this is not the reality. Continuing with chromium, we know that a d subshell can hold a maximum of 10 electrons, meaning having exactly 5 electrons makes it perfectly half-filled. To achieve this extra stability, one electron from the 4s orbital shifts into the 3d orbital. The 4s orbital is now half-filled with 1 electron, and the 3d orbital is perfectly half-filled with 5 electrons. This gives us the true experimentally verified configuration of chromium. This arrangement has a lower overall energy due to symmetrical electron distribution and high exchange energy, proving that atoms will always pursue the lowest possible energy state. Now that we understand both the rules and the exceptions, we must recognize why this matters. Understanding the Aufbau principle is the absolute foundation of all chemistry. It is the very reason the periodic table is shaped the way it is, divided into S, P, D, and F blocks. By knowing the outermost electrons, we can predict exactly how an element will behave in the real world. It tells us why sodium explodes in water while neon does nothing at all. Without this knowledge, we could never design new pharmaceutical drugs, create better batteries, or understand advanced materials. We have covered a lot of ground today, so let us summarize the most important ideas. First, the Aufbau principle dictates that electrons fill atomic orbitals starting from the lowest energy level to the highest. Second, this filling order is mathematically guided by the N plus L rule, where lower sums mean lower energy. Finally, while this rule is highly successful, atoms like chromium will violate it to achieve the superior stability of half-filled or fully filled subshells. You now have the foundational tools to understand atomic structure and chemical bonding. Great job!